Hello friends, in continuation with the last lecture, today we are going to talk about the linearly graded junction. Okay, so today we talk about the linearly graded junction. Again we come back to the place where the two regions are just connected. Okay, it is P and N regions are just connected at the point, and it is forming the depletion region. Okay, so the now here in practical devices, what is happening actually, the doping profiles are not actually whatever the abruptly just changing. Okay, is the doping profile this is something like suddenly just getting changed, and concentration is getting changed over there, right. So the doping profiles are not abrupt, especially near the when the junction is forming or metallurgical junction. Okay, so the two different types of the regions are getting connected to each other. Okay, and they actually compensate each other. So metallurgical junctions where the two types meet and they compensate each other when the depletion widths terminate. Okay, here the depletion widths terminate within this region. Okay, where they are just trying to compensate, two regions are trying to just compensate each other. Okay, so within this transition region, the doping profile can be approximated by a linear function. Means this uh, doping profiles can be actually approximated with the linear function that you can see over here. Now this is the N region and the P region. So these are the something like impurities on the P side region, and these are the impurities on the N side region. So this is what they are having within it, and the width of the depletion region is completely is WD, but on the P side this minus WD by D, because we are just considering the center as a 0. Okay. So now the Poisson's equation in this case is given by, that is minus d2 psi I by dx square is equal to, this is nothing but the double derivative of its intrinsic potential. So this is also equal to the first derivative of the electric field or the electric field gradient. This is given by the rho of x upon epsilon s, right. Now this rho is the carrier concentration density, right, charge density we are just talking about, right. So this can be also written as rho of x is equal to the q, okay, q times okay, this is the charge present over there, right, and P is the hole concentration minus N is the electron concentration plus this linearly graded junction, right, the profile which is approximated as a linear function, right. So some A is some constant, okay, proportionality constant we can consider, right. So but now within this region the charges are equal and opposite, right. So what will happen, this will get this concentration gets nullified each other, because we are within depletion region and it got compensated with each other. Okay, so P and N gets cancelled with each other, so that becomes a 0 because no excessive charges are present. So whatever the left will be, the density will be the q times A into x. So I will just try to substitute this equation within the above equation, that is minus WD by 2 to x. X is which is varying from minus WD by 2 to plus WD by 2 plus WD by 2. Okay. So I just try to rewrite the equation again, minus d2 psi I by dx square, which is I am just approximating it to the qax upon epsilon s. Okay. So I call it as equation number 1. Right. Now obviously this A is some doping gradient, okay, is doping as this related terminology, and if we just try to integrate it, okay, if we try to integrate the double derivative of the potential, we will get the electric field, okay, or else we can have integration of the electric field gradient, we will get the electric field, right, electric field distribution. So the electric field distribution can be calculated as 0 to E, and dE is equal to q q a upon epsilon s integration from minus w d by 2 to some arbitrary x, means we will be somewhere within this depletion region. Okay, I just call it as somewhere here and represented as x. Okay, so we will be somewhere here. So, okay, so corresponding the variable is x, right. So, this will be given as something like a x dx. So, this will result us into the electric field E is equal to q a upon epsilon s into, just write x square by 2, right, x square by 2. So, just try to substitute the values within itself and uh, just solve it. So, what we will get it, nothing but the x square by 2. So, this is nothing but the 2 times epsilon s and then the w d by 2 square minus x square. Okay, this is what we are supposed to get it for the over the given period. Okay, so this is equation number 2. Now, at x is equal to 0, what we will get? We will get the maximum electric field. So, at x is equal to 0, we will get the maximum electric field, and that is nothing but it is represented with the EM. So, what is it? Q A W d square upon 8 epsilon s, 8 epsilon s. So, you can see over here. So, this is the equation of something like we call it as a half circle, right, half circle it has having. So, it goes behavior like this. So, electric field distribution can be seen over this diagram, that is a half circle, it is below the x axis, okay, below the x axis. So, and the maximum electric field is at the center, okay, at the junction between the two regions. So, electric maximum electric field is nothing but the q a w d square by 8 epsilon s. Okay, so, this is equation number 3 I can give us. So, again now this is a electric field. Now, electric field is nothing but the electric field can be calculated from the potential, right. So, potential gradient can be electric field. So, if we try to integrate the potential gradient, we will get the yeah, corresponding potential, right. So, what we will do? We will try to understand the potential distribution also. Okay. So, the once again integrating to obtain potential distribution. So, what we will get it? This will result us into the psi I of x. Again, just trying to integrate this equation, okay, trying to integrate this equation and just considering. So, the equation number 2. So, just trying to consider this arbitrary electric field. So, this is a function of x, electric field is a function of x. So, trying to just integrate the electric field to obtain the potential. Okay. So, what we will get? Q A upon 6 epsilon s into 2 times w d cube. I am just trying directly writing down the integration plus is simple integration. So, 3 times w d by 2 square x minus x cube. So, again the width remains the same, w d by 2 is varying between these plus w d by 2 to minus w d by 2. Okay. So, this is equation number 4. So, from this equation what we will get it? The built in potential can be related to the depletion width. Okay. So, what we know? We know that built in potential can be related to what? Depletion width. Okay. Depletion width. that is x is equal to 0, try to substitute, then we will get the built in potential, that is psi b I is equal to q a w d cube upon 12 epsilon s. So, this is equation number 5. So, built in potential can be calculated from this equation, just substitute the value of x is equal to 0 at the boundary between the two regions. So, from this equation we can calculate the W d as well, or else W d is equal to 12 epsilon s psi b I upon q a raised to 1/3. Okay. So, this is equation number 6 can give. So, since the values of the impurity concentration at the edges of the depletion width, that is at the here. Okay. So, this is what we will get it, the depletion width goes on here, and above the x you can have the maximum psi b I built in potential. Okay. So, and the area of this electric field also gives us the built in potential, right. So, now the since the values of the impurity concentration at the edge of the depletion width, means somewhere here, okay, we are talking about, or else at this point, okay, the minus W d by 2 to plus W by d are the same and equal to the plus W d by, because it is something like the replica of the one of the other one. So, the built in potential of the linearly graded can be approximated by the similar kind of the expression, the equation, that is to the abrupt junction potential. So, psi b I of x can be approximated to the abrupt junction potential, that is k T by q ln and what a w d by 2 into a w d by 2 upon n I square. So, this is something like earlier we have seen. So, this can be approximated something to be k T by q of ln a w d upon 2 n I. So, this gives us the equation number 7. So, this is a psi b I. Okay. So, this from this above to equation number 6 and the 7 can thus be used to solve the equation for the W d for the W d. So, we can substitute the value of the psi b I in the above equation number 6 and solve for the W d. For solving for W d. So, what we get it? So, W d, solving for this W d and the psi b. So, what we can get it? Okay, W d and psi b I. Okay. So, we can substitute this value and try to find out the value of the W d I. Okay. And then the based on the an accurate numerical technique, the built in potential can be calculated explicitly by the expression of the voltage gradient, and that voltage gradient, okay. So, the voltage gradient phi g is given to be the is direct expressions 2 k T by 3 q ln of a epsilon s k T upon 8 n I cube q square. So, this is nothing but the gradient voltage, okay, gradient voltage. So, this is gradient voltage, okay, phi g. So, the depletion layer capacitance for the graded junction is given by, so the depletion layer capacitance for linearly graded junction is, okay, that is what the C d is equal to epsilon s upon W d. So, try to substitute the value of the epsilon s in this case, what is W d. So and I just try to rewrite the equation for the W d in terms of the okay. So what it is, so epsilon s psi b I upon q a, and we can substitute the value of the psi b I, okay, and try to solve this for the for the C d is equal to q a epsilon s square, take this inside, so we'll get it something like 12 psi b I minus phi. Now there is a sudden uh, change of the some kind of the our equation, okay. So what it is, that is nothing but the when this is equation when there is a no biasing of the biasing potential is not applied in this case, but here we can just try to bias the our junction by applying whether the positive potential or the negative potential, or the or else so we can have the forward bias potential or the reverse bias potential. So this is the linearly graded uh, junction, okay. So the potential and the capacitance for corresponding to it. So you can see the potential distribution in this case is to be something like increasing, and it will get saturated for this potential, or else on the other hand this is what we can call it as a potential distribution, or else the energy band diagram is something related to this, so related to the linearly graded junction. So what we can see, the Eg is just decreasing here because this is inside region. So obviously the Fermi level will lie near to the conduction band, and in case of the P region, the Fermi level is something like we call it as a very much far. The conduction band is far away from the Fermi level in case of the linearly graded junction. Yeah, we stop here.